This is the first video for section 7.4 covering vectors. We're going to break this section up into a few different videos because it is a significantly large topic here. But the big idea behind vectors is that some quantities that we want to describe have not just a number to them, like a size to them, but also a direction to them. For example, if I want to describe how I don't know, snowflakes falling from the sky are falling, there are kind of two important pieces of information: the fact that they fall in a certain direction and how fast they fall. So that is a quantity. How something moves is a quantity that we'd want to express with a vector. And that in particular we typically describe with what we call a velocity vector. But let's jump in here with the basic definition. Now that we have these certain quantities called vectors that describe both quantities that have both a direction and a magnitude, a size to them, we need to distinguish between the types of objects we've talked about in the past. In the past, we've talked about plain old numbers that don't have a direction to them, just have a magnitude to them. Well, here we call those scalars, just to differentiate between vectors, right? So if I'm talking about regular old numbers, I'll call them scalars. If I'm talking about vectors, I'll call them vectors. When we're talking about a scalar or a vector, we typically call how big it is the magnitude. For a number, that's just the absolute value. Right, this is sort of the example I was describing. The speed of an object is a scalar, because when we say speed, it just talks about how fast something's traveling, not about a direction it's traveling in. But velocity, we want to be a vector because it has a direction. Things move in a certain direction and has a certain speed with which it moves in that direction. So let's start. You can generalize the idea of vectors to higher dimensional spaces, not just 2 dimensions, but we're going to stick with a 2D picture, just vectors located in a plane. And for those, we really just define them to be a line segment with a specified direction to it. So for example, if I have 2 points P and Q over here on the side of my picture, we can define a vector from P to Q. We would call that the vector PQ with this little hat on it to denote that it's a vector quantity. The length of that distance, right, the distance between P and Q, the length of that vector, we denote with these double bars here. You might hear that be called a magnitude of the vector, or a norm, or modulus again, like we saw in complex numbers. We won't usually use that here. We'll call this magnitude pretty often. But really, that's all you need to make a vector. Visually, all we need is to say we start at one point and end at another point. We can draw an arrow, and we think of that arrow representing a length and a direction, or the direction we moved in and how far we moved. So magnitude and direction represented in an arrow. So it is useful to think about how we might use these vectors. This is pretty useful here to think of a vector as a displacement, a change in position. If we wanted to describe how an object changes its position and it started at a point P and ended up at a point Q, we could describe that overall displacement of that object, the change in its position, by this vector. It tells us how far we moved and in what direction we moved. Now, it's going to be pretty useful to think of vectors very often as being what I would describe as untethered in space. If I draw one of these little arrows anywhere in space, so long as I don't rotate it or change its length, I can draw it anywhere else in space and it's still the same vector. That's what we really want to understand, is that when we give labels to a vector, we're really describing every possible line segment with a direction to it that has the same direction and the same length of that line segment. So, for example, in this picture, all these look like the same vector v to me. That is pretty common. And when we are denoting vectors, usually in print they'll be in boldface lowercase letters like U, V, and W here. If we're describing it as a displacement from one point to another, we'll describe it as something like this. V equals A to B with the little arrow over, a little vector hat there. Right, but when we describe V equals the displacement from A to B vector here, we're really thinking of any arrow that is parallel to that arrow and has the same length. That visual picture would represent the same vector. It makes a good point here, though. It is hard to write in boldface, so usually when we write arrows down, we'll go ahead and put that vector hat on top of it if we're writing by hand, because it's hard to show boldface by hand. And it is important to denote a vector when you've got one, whether it's in boldface or with these little harpoons on top, these little vector hats. It's important to denote a vector quantity versus a scalar quantity when you're working with it. So let's look at this first problem here. It says, determine if the two vectors are equal. Let's start here. Vector v from negative 3, 1 to 1, 4, and vector w from 0, negative 3 to 4, 0. So remember that we are just saying, sketch these points. Let me see if I can sketch these points. Negative 3, 1 to 1, 4. That's one of our vectors. Oops, a little off there. It's very tricky to draw these on a computer. There you go. That's good enough. That's one of these vectors. That's this vector v. And let's see. Let me label that. Vector w goes from 0, negative 3 to 4, 0. And we're asking, is this the same vector? Are these two vectors equal? Well, notice this one goes up 2 over 4. This one goes up 3 over 4. They are not pointing in the exact same direction. This one's tilted a little more vertically than this one is. That's a different direction, so it's a different vector. V does not equal W. Let's do the same sort of thing with the next part here. Let's look at the next two, A and B vectors. Oops. Sorry about that. Let's look at these A and B vectors from negative 4, negative 2. And maybe now's a good time to pause the video, see if you can do this on your own first. I'm going to keep at it though. From this point to negative 1, negative 4. So this is a vector. This is a vector pointing in this direction. That's vector A. The other vector is pointing from 4, 2 to 1, 4. Now, are those equal? You might say, well, those segments, those are parallel, and they are. Those segments connecting the 2 points, those are parallel. But notice, well, in more than that, they're the same length, right? You go down 2 over 3, down 2 over 3. That's the same little triangle here as you have here. That's the same length between your points. A and B have the same modulus. So we're going to say that, first of all. But are they equal? Notice one starts higher in the plane and goes lower in the plane. The other starts higher in the plane, starts lower in the plane and goes higher. These are in opposite directions. I would say A is not equal to B. And in fact, this is a nice time to realize that somehow these are very closely related. One is just the opposite of the other. In numbers, scalars, we would say that one is the negative of the other. We'll see that's the same for this situation. Let's talk a little bit more concept here, more about displacements. We want to think about what it would mean to add some of these vectors. And since we're just describing these vector quantities as pictures on a plane, pictures on a piece of paper, we need to describe addition or subtraction arithmetic on these in terms of those pictures. So if vector v represents the displacement from p to q, so that's this vector from p to q in black here, and vector w represents the displacement from q to r, here to here, then the vector v plus w, the sum of these two, we define it to be just overall what your displacement was if you first made a change of position from p to q, that's the v vector, and then in sequence after that made a displacement from q to r, traveled along the direction and length of that vector w. One displacement after another means overall you started at p and went to r, so the vector from there to there should be the sum of those two. Right, you took some weird steps to get there, but you went from here, then to here. Overall, you went from here to here. That's the idea. So we call the overall beginning point to the overall end point the sum of these two vectors. When we talk about forces as vectors, we usually call that sum a resultant vector. A resultant. So the vector v plus w is formed by placing v and w tip to tail. So remember, these vectors, v and w, they might be given all over the plane. Maybe one's over here and one's given over here. You have to redraw them tip to tail. Don't rotate or change their length. Just translate them in space and redraw them tip to tail. Move that guy over there. Let me just erase that. That's misleading. Redraw them tip to tail. The initial point of w, so the point where w vector starts, is placed at the terminal point of v, the place where v ends. P is the initial point of v, q is the terminal point of v, q is the initial point of w, and r is the terminal point of w. The initial point of the first vector in the sum to the terminal point in the second vector in the sum is the sum vector, p to r in this case. It's a lot to say outright, but visually I think is the best way to think of it. So you can think of it by putting these guys, oh, sorry. I described up here what's happening down here. Sorry about that. The key for this method, this triangle method, for adding vectors is to place these guys tip to tail. Draw v, from the end of v, draw w. The overall displacement is v plus w. What it's saying down here is there's actually a different way you can also add vectors, and that is to think of putting them instead, like I drew up here, putting them tail to tail. So initial point to initial point to initial point. Then you can think of them as kind of sweeping out this parallelogram. Well, the diagonal of that parallelogram is the sum of your two vectors. It's exactly equivalent to looking at it through this triangle method. Sometimes this down here is called the parallelogram method. What comes next is something we've already talked about a little bit above, that it gets at this idea of an opposite. Right. So let's see what we mean by an opposite. We are going to say the vector negative v is just the scalar negative 1 multiplied on v. But keep in mind, we actually don't know what multiplying a vector by a number really means yet. So I think all of this is way out of order. I think this is out of order. First, let's talk about what's down here. What it means to multiply a real number, a scalar, onto a vector. Scalar k times vector v. Let's see visually what we think of as representing. Then we'll go back up and talk about what we're skipping. So let's see here. The value k is a scalar, and for this reason, when we multiply that number, k is just a real number, just a scalar. Usual numbers that we're used to dealing with. Multiplied on a vector v, we call that a scalar multiple of v. all that does, it's scaled. When we multiply a vector by a scalar, it scales the size of the vector. It stretches or shrinks the length, right? The magnitude, by a factor of whatever the absolute value of that scalar is. If you multiply a vector by the zero vector, it's going to be just the zero vector you get out, which has got no magnitude and no direction to it. So that's kind of a special case. Don't really worry about that so much. Up here is more what we care about, multiplying by a non-zero scalar. For example, a vector v in blue here would say that would tell us that when we multiply it by 2 to get 2v, it's the same direction, just twice as long. If we multiplied vector v in blue by a half to get a half v, that's just the same direction but half as long. If we reverse the direction, that means taking a negative here, which is something we kind of referred to in that previous example, where we were seeing if two vectors were equal and they look to be opposites of each other. V times negative 2v, is twice as long as v, but the opposite direction. And negative a half v, for example, would be opposite direction and half as long. So now that we know what scalar multiples really are, what it means to multiply a vector by a scalar, now we can come up here and make sense of what is being said here. I guess what's being said here. Now we know what it means to say that negative of a vector is defined to be negative 1 times that vector. It means that v points in one direction, negative v, this by our scalar multiple rules, is just negative 1 times that vector. It just has the same length but opposite direction. Same length, opposite direction. So now we know what it means by what we mean by negative of a vector. We mean same length, opposite direction. And this is how, now that we have the idea of a negative vector, this is how we actually describe subtraction of vectors. We can say v minus w is just, well, I guess it's written here, but I'll go and finish what I'm writing. Adding a negative. That makes sense. We're going to go and define that that's how we think of subtraction for vectors. It makes sense for numbers. Let's apply that here and define this to be the subtraction rule. It's like adding the opposite of w to v. Well, then that's easy. If I want to add the opposite of w to v, say I've got my vectors here. My vector v in the middle here. If I was to add w, that would go this way. I'm saying w looks like it's in this direction. Well, we want to add negative w, so we're going down here, right? We're going the opposite direction, the same length. Connecting up where we started to where we ended up, we get that this v minus w, which is really v plus negative w. Right? V plus negative w gives us this little length here. Now visually, I think it's easiest to subtract vectors with the parallelogram rule, which is just to put them tail to tail like in this picture, and think of the parallelogram swept out. We know that the long distance across from their common tail across is the sum of the vectors. It turns out connecting their tips is the difference of the vectors. And this kind of makes sense. I would think of subtracting my vectors, subtracting two vectors, maybe a and b. What does it mean to subtract two numbers? It's finding what's between them, right? How much is between them? Well, same idea here. I've got one vector pointing out here, one out here. I want to see what's between them. I want to connect what's between the tips of these vectors to get their difference. And you might say, well, how do I remember which is which? Is this direction from the tip of B to the tip of A, is that A minus B or B minus A? Because they're going to be opposites, right? A minus B is the opposite of B minus A. Well, I'll tell you, the easiest way to remember is just by thinking, if I want A minus B, the vector that I finish with better point to the first vector in that. It points to the positive one. So if I'm doing A minus B, I'm going to point toward the tip of A. If I wanted B minus A, I would point toward the tip of B. Right? And you'll see these are opposites of each other. They're just opposite directions, which makes sense with usual math. Subtracting the opposite direction, you get the opposite number. Right, so that's how we want to think about subtraction. We said here that scalar multiplication really just scales the length. That is what is said in a little more detail mathematically here. When I multiply a vector times a scalar, its magnitude is the size of the scalar times the size of the vector. Okay. So let's see a couple examples real quick before we break for the next video. Let's sketch u plus v by placing the initial point of u at the terminal point of v. Easy enough. U plus v by placing the initial point of u, so the point having u start at the terminal point of v, where v ends. V ends here. I want to draw this vector that goes from there, goes 1, 2, 3 down, 1, 2, 3 over. 1, 2, 3 down, 1, 2, 3 over. To there. That's another copy of u drawn with its initial point at the terminal point of v. We know when we do this to add our vectors, we go from our first initial point of the first vector to the terminal point of our last vector in the sum. And u plus v and v plus u are the same, so it doesn't matter which order we consider this. Oops. There we go. That is the sum u plus v. It's important to notice the difference matters which order you do it in, but a sum doesn't matter. Okay. Parallelogram method or triangle method would give you the same vector when you add vectors if you do u plus v or v plus u. So I added those here. Let's sketch u plus v by drawing u and v with the same initial point. Well, so let's, I figure, just draw u with the same initial point as v. Let's notice u goes from 6 down to -2. That's a drop of 8 units. So we'll go from 2 down to -6 down here. And it looks like the run, the amount it changes in the x direction, is -6 to -3, so that's +3. We need to go down 8 over 3. So let's see what we get. It's rough, but that's my vector. And so we know to add these from drawing tail to tail this way, we need to repeat each of these vectors to kind of complete this parallelogram. And this is going to go a little bit down further than what the graph shows, but that's okay. We know if we have them tail to tail and we kind of complete that parallelogram that they've started, then going all the way across there gives us the sum. This guy over here was u repeated. Right, so that's not bad. You can figure out where that would land, but it's okay. Let's just leave this. Let's sketch v minus u by drawing v and w with the same initial point. So I'll draw w with the same initial point as v, just to draw in a convenient place. So starting from here, I need to go 1, 2, 3, 4 down and 2 over. 4 down and 2 over. That's my vector w. And if we want v minus w, we talked about how to do this. We remember that the sum, or the difference vector, always connects the tips. If we draw them tail to tail, it connects the tips of the two vectors, and it points toward the first one, toward the positive vector. From here, toward the positive vector, the v vector. So this is v minus w. I don't think these ones over here in problem 5 are going to be too bad. This will be the last one we do with this video. Let's see what we can do. -2v and 3w in standard position. So standard position just means draw the tail at the origin. So for example, -2v, we can make that note. Tail at the origin is what we mean. So let's do negative 2v. That should be a vector at the origin that has this, notice this vector goes back to down 3. Back to down 3. So v in standard position would look like this. We want to draw negative 2v. So it should be twice as long and go in the opposite direction. Instead of going back 2 and down 3, let's go forward 2 and up 3. That's the direction we want to travel in. But we want to go twice as far as this guy. So I'll do this twice actually. That's negative 2v. Let me erase this guy. That's our answer there. 3w is just this w vector except 3 times as long. So draw that guy with its tail at the origin, the same point here. And we want to go, w goes over 2, up 2. So it's going to follow the over 2, up 2, over 2, up 2, over 2, up 2. We want it to be 3 times as long. So let's go over 6, up 6 instead of over 2, up 2. That vector there that follows along that slope of 1 to 1, rise to run, that is 3w in standard position. Remember, standard position just meaning tail at the origin. Let's stop this video here and pick up trying to express vectors more algebraically, not just in pictures, but actually as symbols. Let's see how we do that in the next video.